What I will try to do is to give you an introduction of the kind of work that we've been doing in IH Cantabria, a series of researchers within the Institute. We've been focusing mostly on trying to address some of the problems that you have to face if you want to develop offshore wind energy. That, as you know, the degree of matureness that already achieved is much larger than other of the energies we are considering within this project. Probably those of you who have been interested in this topic may know that during the last 15 years, the total wind power installed in Europe has increased in 33 times. So really, there has been a serious development in offshore wind energy. In 1995, wind power installed was 2.5 megawatts, 2010, 84,278 megawatts. And in some of the figures that we've seen from Mike before, we see there is a lot of potential in many of the European countries for the development of offshore wind. But the most important thing is that the yearly installed offshore wind power has increased from 0.1% in 2000 to 10.5% in 2010. So meaning that in 2000, the power installed was 4 megawatts, which is more or less the size of one of the standard turbines this industry is considering right now. And in 2010, the power installed was 883 megawatts. So basically, we've been trying to work in all the different activities within the Marine project that were presented by Mike at the beginning, trying to contribute from our experience and perspective and how the different issues need to be tackled when you're considering offshore wind energy. So we have contributed, as you will see, to the comparison and knowledge exchanges of experiences. We've been fortunate because there are a lot of different experiences and farms that have been already built. We've been working on the assessment of the energy extraction potential. This is, again, a huge problem, very different from the one that Roger was just showing. We cannot predict, as tides can be predicted, how the winds and waves will behave. The probability is a big issue. It's not a deterministic approach, and that's very complicated, and that's the reason because we have devoted a large amount of effort within the project in trying to establish how to evaluate these resources properly. Then how to use this information for the assessment of the hydro-environmental impacts. And finally, we've been looking together with the people here in Galway, what are going to be like the impacts of climate change on the design requirements and the resources of offshore wind power. So the first thing was just to have a review of what is the current state of the art in offshore offshore wind development. So we have put together a report that you will be able to find on the web page. Basically, what you see here on my left is what is the contents. We've been starting showing some project examples with different foundations. We've been discussing what are the offshore wind power costs, which is the main issue that's now facing industry. To give you an idea of the differences, when we are talking of offshore wind, we're talking about up to 3 million euros per megawatt. And if we're talking about wind energy and land, we can talk about 1 million. So it can be 2 to 3 times the cost that we have in land development. Then we have also discussed some other issues like what is the contribution to GHG emissions, the technology overview, and basically we have tried to see what are the differences of gravity-based, tripod, monopile, jacket foundations, combined foundations, and then we've been also considering other schemes, basically spar buoys and semi-submersible. As you know, most of the development nowadays is taking place in the north of Europe. Scotland, the UK, and the Baltic are some of the areas where most of the offshore wind energy is developed, and this is mostly because they have shallow water. But there are many other countries, not only in Europe, but all over the world, where the shelf is very narrow. And therefore, if we want to have visual impacts, we need to go to deep waters. And this means that we have to move into jacket solutions, or we have to move into floating devices. And as you see, Ireland has already evaluated what is the potential of these floating devices. Here you can also see already some of these floating devices like high wind. This has been already built by Statoil and has been in service for the last 2 years. It's a very small turbine, if I remember correctly, 2.3 megawatts, and the cost was about 70 million euros, but it's working, so the technology is there. The problem is it's still too expensive, and you see some other solutions that are now undergoing. So most of the information has been introduced into the web page, as Mike was already showing. And precisely, if we talk about the information that you will find in the web page on offshore energy, you will see offshore wind farms, the most relevant milestones. Where are these farms? What is the size of the farms? What is the energy in these farms? What kind of turbines? What kind of foundations? If bottom fixed, shallow water, transitional waters. You will also find information on floating concepts, what kind of turbine prototypes they are using, if they are considering multi-platforms for deep waters or other kind of solutions. And you will also find some other additional information that we thought that was very interesting for those of you who want to get involved in this topic. Basically, where are the demonstration test sites, infrastructures worldwide, or what are the most relevant R&D projects? What are the consortiums carrying out these projects, the networks and technology transfer efforts that are now undergoing? So the second contribution was mainly to see what is the experience in Spain, and I don't want to say much about this because Mike has given us a very good summary of this. Now the only point that I would like to make is that Spain has a new national renewable energy plan from 2011 to 2020. Unfortunately, offshore energy is not relevant for this plan, and the only plan is to develop about 200 megawatts in wave energy by 2020. This may be due by several factors. The financial crisis, we got a cut of all economic incentives, the feed-in tariff for the development of any new renewable energy infrastructure in January 2012, and also due to the fact that land wind energy is very, very developed in Spain. In fact, we have come to a point in which 20% of our energy demand is covered by wind energy. So the second activity, it's been the one where we have mostly I think, some interesting contributions, and is on the assessment of the energy extraction potential. Basically, the wind resource assessment is the first step if you want to develop an offshore wind farm project. And the goal of the work that we've been doing was to reduce the project uncertainties by trying to evaluate properly and precisely what is the wind energy production, trying to reduce the uncertainties, how this information can be used for operation and maintenance, which is also very relevant, the structure and turbine design, how is this going to be affected by the wind loads. And in order to do this, the problem is that you need to provide not only winds. The main problem with offshore wind farms is that you need to provide winds, but also waves, currents, barometric pressure, temperature, rain, visibility. So there are a lot of geophysical variables that need to be provided, and the problem is that you need to predict them. So basically what we started doing is just make a review of what was the requirements in terms of wind assessment for most common recommendations and specifications. So you have a few of them here. Of course, offshore wind energy is very much connected to oil and gas. Most of the recommendations stem from there. And there are several ones for the design requirements for offshore wind turbines, design of offshore wind turbine structures by Dernosca Veritas, rules and guidelines for certification of offshore wind turbines, and other recommendations by Danish Energy Agency. So basically what we have done is try to see what are the recommendations and see what is the state of the art in our knowledge of the evaluation of these geophysical variables compared to what is asked for in these recommendations. So to give you just one example, here is one of the recommendations, and the recommended mid-ocean database are wind speeds and directions, significant wave height, wave periods and directions, correlation of wind and wave statistics, which is very relevant, and depending on the site's current speeds and directions may also play a very relevant role. Of course, water levels, occurrence and properties of sea ice and icing. Think about the fact that some of these farms are deployed in Northern Europe. Air and water temperature, salinity, marine growth. There are some of the issues that need to be covered. And there are some specifications, like the case of the wind turbine. They want to know about extreme 10 minutes average wind speed at the hub height with a recurrence period of 50 years. So there is a lot of information that's required, basically defining some specific statistics that need to be provided if you really want to be using this information for design. So basically what we have done is we have developed a methodology in which the assessment is carried out in two steps. The first one is using this geophysical information or atmospheric information or ocean information for wind farm projects. So the kind of information you need for site selection and site characterization may depend on the location, the distance from the coast for the efficiency and the costs. The bathymetry may give you what is the kind of technical solution, of course, in the geotechnics. And the wind conditions may give you an estimate of what is going to be the investment return time. So this is just information that can be provided by given information from hindcast databases. And there is a second step, which is the site characterization, in which you need to provide information for wind turbine design and certification, wind farm layout design, operation and maintenance plans, financial and economic assessment, and this is a much more higher resolution information. And therefore, there are much more challenges in providing this kind of information. So this is basically what we've been doing. We started from global information and tried to see what are the best methodologies to downscale it to local offshore wind farm. And using mesoscale models, you end up using CFD models when you want to look into the loads on the turbines. We developed a methodology for this that has been published in some conferences as part of the MARIN project. So basically the idea is that you will start from global wind fields. And you, of course, want to have long time series. You want to have historical records to know how different variabilities may affect the farm. So based on this, we do a downscaling with wind fields, and what we do is give recommendations on how to select the numerical model and some other technical issues on what is going to be the grid, like recommended, the topography, what kind of boundary conditions need to be used, and also a sensitivity analysis of some of the physical parameterizations that are required for the, mostly for the atmospheric models. So we have also give some ideas on how to use anemometers or even satellite data, not only to do validation, but also to do calibration. And validation, in fact, has been carried out also with meteor masts. We have developed also, as part of a spin-off in the university, a floating met mast that is giving you measurements up to 110 meters. So we have used all this information to have an integrated approach to determine how to obtain at the end wind climate and how to obtain a wind energy atlas and wind climatology, as will be shown. So this is just an example of how we get from the INCEP global reanalysis to a high sea wind resolution, we call it sea wind, for a given area of interest, in this case the area of interest of the MARIN project, and in the end you get to a higher resolution, what we call the sea wind high resolution data for the north of Spain. Of course, when you go to a farm, you have even to downscale even more up to a nautical mile, for example. So these are some of the databases. As you see, the time periods go from 1948 to 2009. Why so long? Industry usually is not interested in such long time records. They say that 10 years, 15 years is enough. If you offer them more, they will ask you for more. The good thing about this having long time series is that they are very useful to understand the different time scales of variability. And as you will see, this is ending up in some important changes during the life cycle of the wave farm. So at the end, what we end up is providing time series. Here you can see time series 60 years of wind intensity or wind direction. So we have connected this with the hydroenvironmental impact, going directly to the link with what we said before. Here we have a scheme from NRL in which you see essentially for the floating device, the kind of problems that you have to face and the kind of mid-ocean information that you need. As I said before, wind, waves, currents, lightning, turbulence. So there are a lot of challenges that need to be provided. So we have been looking into what are the initial load cases that are required by industry, and as you see, it's a combination of waves, wind, and currents. And again, you have the problem that you need to provide the required modeling to give information at these different scales. So we've been doing some cases, and at the end, we end up publishing a paper in Renewable Energy for offshore wind farm layout optimization using mathematical programming techniques, in which basically we say how to use this information and how to use the right models to provide this information. Another challenge also is that most of these turbines are increasing size. Increasing size means that we will need higher and higher towers. Here you see one in which we're talking about 100 meters. Usually the information that we get from instrumentation is at 10 meters height. And therefore, what we have to do is, even if we have numerical models, many times what we have to do is we have to extract and extend this information up to 100 meters. So what we've been doing within the project is trying to look into what are the best parameterizations and models currently available to extend the information from 10 meters up to 100 meters. So most of this information, you will find it in the web page. This is the web page that Mike was trying to show you before. Now it's linked to our Institute web page, but it's going to be moved to the Marine Project web page. So essentially what you can see is on Google the projections of the resources. You have winds, you have tides, you have waves that have been generated within the project. And in the case of the wind, you will see that you have wind at different heights, 10 meters, 30 meters, up to 80 meters. For different selected test sites, what we have done is develop this kind of maps in which you have more detailed information. You have probability distributions for mean conditions, for extreme conditions. We've been looking into the monthly distribution, the different directions. We have developed time series, and also we have developed complete wind profiles that can be used for the assessment at different heights. So the final part of the talk is going to be devoted on climate change impact on design requirements. So basically, the issue here is that we know that atmospheric circulation is generating winds, it's generating waves, and it's also somehow generating currents. And this is going to be affecting the potential power that we have for waves and that we have for winds. In this case, we've been focusing mostly on how climate change is going to be affecting potential power, and at the end, how this is going to be affecting the expected extracted power by the turbines. Because at the end, if you're thinking that the life cycle of one of these farms is going to be about 30 years, the problem that you will be having is that you're doing all your calculations based on historical information from the last 20, 30, 40 years, but you want to extend life cycle up to 30 years in the future. Therefore, you should take this into account. And I will show you this. So basically, the idea is that when we have been doing this, we've been looking into how the resources are going to be changing, but we wanted to link it directly to the wave farms. So at the end, what we are doing is not only calculating the wave power, but also how the wave power is going to be extracted by each of the different turbines. So within the modeling that we are proposing, we are also integrating schemes like the ones that you see here, in which basically this is the Alpha Ventus Park farm, which is in Germany, in which you have 3, 6, 9, 12 turbines located very closely. So you have here effect of the shadow that's created by each of the different turbines. So basically what we have done is generated a model to take into account how each of the different turbines are affecting the other ones. And when we've been looking into how this is going to be affecting production, we have introduced this kind of modeling to really try to see what is the direct effect, not on the resources globally, but on the turbine. So what has been the starting point? The starting point has been to use general circulation models or global climate models. And we've been using the very last ones, the Coupled Model Intercomparison Project Phase 5. There, for those of you who are familiar with this kind of modeling, this is the family of models and results that has been currently used by IPCC for the fifth assessment report. So the objective, the first one was, well, we wanted to develop a methodology to evaluate the skills. There are tons of models available. There are tons of results, but none of them are good, and none of them are good for the kind of questions we were asking for the models and for the region we wanted to be working, which was the region covered by the project. So what we have tried to do is to evaluate what are the skills of these models to reproduce the most important synoptic situations. The second one was to see the skill of these models to reproduce the historical interannual timescale variability and the consistency of the models for the 21st century projections, and choose what were the best models available for the Atlantic region and see how they can be used to see how the projected wind and wind power resources are going to be changing. So basically what we have done is we've considered several representative concentration pathways. So this is essentially what in previous years was called the different scenarios. And to give you just an idea, RCP 4.5 means a scenario in which we assume there is going to be moderate mitigation. For a case RCP 8.5, this means low mitigation. So industrial development will continue. We won't mitigate that much. We will continue with a lot of emissions. So basically what we have done is we have used and select the right models to see what we have called present conditions. So how the wind and wind power has changed from 1961 to 2000, and compare it with the projections from 2061 to 2100. So based on the analysis of the skill, we've been analyzing about 26 different models, but we have chosen the 4 ones that you see here. We have prepared a draft of a paper in which we explain how has been the process to select the right ones. But these 4 ones that you see here right in the middle of it are the ones that we consider to be the best for this application. So these are some of the results. What you have on the top is the result for these 4 models, starting from the left to the right, the different ones. And what we are plotting in here is what is the difference between the mean annual wind expected from 2061 to 2100 and the difference what we have called the present conditions. Blue means a reduction in wind intensity, red means an increase in wind intensity. So what you see really is that the different models, they don't give exactly the same results. We won't talk much about this because we could speak for hours. But basically what we see is a certain consistency in the 4 models given an increase in the values in the south of Europe, and also some of them are given increase here on the top, and also a reduction in some other areas. So based on this, what we have integrated all the information to see the differences at a larger scale. If you see the dots, it means that in this parts of the in this grids of the model, there is a very high consistency, and all 4 models are given the same trend. So basically, what you see again is that there is a high increase in this area and some decrease in the UK and Ireland. What is important also is that there are some differences depending on the seasonality. As you know, when you're designing a farm, you don't have to think only on the mean conditions. You have to think on the variability. And in this case, what we've been doing is just looking into how things are going to be changing depending on December, January, February, May, April and March, April, May, and September, October, November, and so on, to see how things are going to be changing. And as you see, the patterns change depending on the season. And also they depend a lot depending on the scenario. It's not the same having moderate mitigation than low mitigation. If we have low mitigation, the changes are much higher. So I'm coming to an end. What is the important thing? The important thing is, and also we've seen this when in some previous presentations, is that changes in wind intensity can be small, but the problem is that power in wind energy goes to the cube of the velocity. And therefore, these changes in stem of power can be very high. And again, here you see the consistent pattern depending on the different projections. For the low mitigation, you see that there is an increase in all the areas where we may be interested in developing these offshore farms. So as a summary, annual wind power shows a general increase along the southern European Atlantic coasts, in the Canary Islands and the Madeira Islands, in Portugal, North Spain, and France. The increase obviously is much larger if we have low mitigations. A significant decrease during the summer is found in the Atlantic marine areas of Ireland, Wales, and England, and a slight decrease has also been obtained during winter season. And a significant increase is found during less energetic seasons in summer and spring in the southern Atlantic European countries. But the most relevant conclusions, and this is my last slide, is that these projected changes may affect the economic feasibility and the life cycle and the operation of management of offshore wind farms. Not only offshore wind farms, the same will happen for the wave farms. Because if you review the literature on projected waves, you see that things are changing already. So what we say is that climate change and climate variability at seasonal and interannual scales should be accounted for in the planning of marine renewable energies in the future. So thank you very much.